Good morning, good afternoon, good evening. This is Odavig Structural Hub, the #1 channel for structural insight and a place where you learn, build, and innovate. Today I want to tackle a problem, and this is a foundation design to BS8110. So it is a pad footing, and the question is on the board, and it reads: a 400 mm square column carries a dead load, which is GK of 1050 kilonewton, and imposed load, which is QK of 300 kilonewton. The self-bearing capacity of the soil is 170 kilonewton per meter. Design a square pad footing to resist the loads, assuming the following materials strengths. So FCU is equal to 35 Newton per millimeter square. Fy is equal to 460 Newton per millimeter square. So this is the footing. So this is the pad footing, and this is the column. So this column is carrying a dead load, which is 1050 kilonewton, and imposed load 300 kilonewton. So let's see how we can tackle such a question. And for those who are watching this video and you have not subscribed to this channel, you are missing a very important content. Please subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. So the first thing to do, I want to write the most important information on this column so that I can rub here and create space for our proceeding calculation. So the GK is equal to 1050 kilonewton. QK is equal to 300 kilonewton, and the self-bearing capacity 170 kilonewton per meter square. FCU is equal to 35 Newton per millimeter square. Fy is equal to 460 Newton per millimeter square. Having done so, I can comfortably rub here so that we can have space for our calculation. So solution: the first thing to do is to calculate the plan area of the base. So calculate plan area of the base. So if this is a column, and this is the base, then we need this area. From this area, we can be able to get the size of this base. So let's say X. Like that. So to calculate the plan area of this base, we will assume a footing weight of 130. So assume a footing weight of 130 kilonewton. You can assume any other weight. It can be 100, 120, 130, and so on. So we have assumed this base it has a weight of 130 kilonewton. Then GK will be self weight of the footing plus 1050 kilonewton. So this is 10, our GK is 1050 kilonewton. Like that. So this one is equal to 130 plus 1050 kilonewton, which imply GK is equal to 1180 kilonewton. This is 1180 kilonewton. And our QK is equal to 300. QK is here, 300 kilonewton. So serviceability load is given by this formula. So which is N, serviceability load So serviceability load is given by design axial which is N is equal to 1.0 GK plus 1.0 QK. So 1.0 times 1180 plus 1.0 times 300. So this one is equal to 1480 kilonewton. So in the introduction to foundation design, I forget to give you this formula, the design load, which is N. So this design load is given by 1.0 QK plus 1.0 GK plus 1.0 QK. And this N, it is used to calculate the area of the footing. So let's proceed. So plan area of the base, is equal to N over self bearing capacity of the soil. This is the formula to calculate the area of the base is equal to N over self bearing capacity of the soil, where N is equal to 1480 kilonewton and self bearing capacity you have been given as 170 kilonewton per meter square. So plan area is equal to N, which is 1480, all over self-bearing capacity is 170. So this one is equal to 8.70 meter square. So this is the area of the base. So this is the area of the base, 8.70 meter square. So we can make it 9. So let's make it 9 meter square so that it can be a perfect square. So 9 meter square. So this is the base. After getting the plan area, we can easily calculate or determine one side of this square base. So to determine one side of the square base, you will get the square root of 9. So one side of the plan is equal to the square root of 9. So which is equal to 3 meters. So if this is, so it means from here to here is 3 meters. So this is elevation. But if you have a plan, this is how it will look like. So from here is 3 meters. Again, from here is 3 meters. So this is a plan. This is elevation. So after calculating the plan area and one side of this footing base, so you will conclude by saying that hence provide a 3 meter square, base. And then in bracket plan area is equal to a 9 meter square. Now you have determined the plan area and the sides of this base. We proceed. So we proceed to self-weight of the footing, self-weight of the footing. Remember, we assumed 130 kilonewton for self-weight of the footing. But since now we have the dimension, we have the area, and we can also assume the depth of the footing, we can easily calculate the weight of this footing. So in short, if this is the plan, the elevation, not plan, and the area is equal to 9 meters square. So what you don't have is this thickness of this base. So assume H to be 600 millimeter. So this H is 600 millimeter. Then the self weight of the base will be area times H times unit weight of concrete. We will assume the unit weight of concrete is 24 kilonewton per meter cubic. So self weight is equal to area is 9 times H 600 over 1000. You change to meters times 24 kilonewton per meter cubic. So which imply self weight is equal to 129.6 kilonewton. Therefore, 129.6 kilonewton is less than 130 kilonewton. This is the one the one we assumed. Now it means we are on the right track. Now we can continue with our designing. So after this, we now proceed to bending reinforcement. Bending reinforcement. Bending reinforcement. So to calculate bending reinforcement, we need the maximum bending moment. Maximum bending moment, which is M. And to get M, we need the following parameters. Total ultimate load. Number one, we need total ultimate load. So which is W. This one is given by 1.4 GK plus 1.6 QK. So W is equal to 1.4 times, we will use this one, 1050 plus 1.6 times 300. So this one is equal to 1950 kilonewton. 1950 kilonewton. So someone can ask, why are we using a GK as 1050 and not the one you calculated as the one you calculated earlier? It was 1180. So this 1180, it is only used for serviceability load. This one is used to calculate the serviceability load, which is 1.0 GK plus 1.0 QK. So this one is equal to N. This one is used to calculate this. And when it comes to the ultimate design load W, use this as GK, not this one. So we proceed. Now we need to calculate the earth pressure. Earth pressure. So this is PS. This is PS. So this is the pressure as a result of this ultimate load on the ground. So this one is equal to W over the plan area, like that. So PS is equal to 1950 over plan area, which is 9. So this is in kilonewton and this is in meter square. So the answer is equal to 217 kilonewton per meter square. So this is the pressure on the ground. We can also draw an elevation showing the dimension and the pressure which we have calculated as 2017 on the ground. So this is the base. And this is the column. So the ground pressure is equal to 2017 kilonewton per meter square. So this is the ground pressure. And remember, this distance from here all the way to here is 3000 millimeter. So it means if we can assume our column is 400 millimeter, then you can also calculate this distance and also this distance. So these two distance will be equal to 3000 minus 400, then divide by 2. So you will get 1300. Having done so like this, we can easily calculate our maximum bending moment, which is M, using this elevation diagram. So let's proceed now to our maximum bending moment M. So design moment, which is M, occur at the faces of column. And remember, this is the M max. So the maximum bending moment M occur at the faces of a column. So if this is a column, then it will occur at the faces, of this column. So this one, M is equal to WL square all over 2, which is equal to, our W is the ground pressure, or is the earth pressure, which is 217, times L. L is this distance from here to here, which is 1.3 square over 2. So remember, moment from the basic moment is equal to force times perpendicular distance. So if the maximum moment is acting at this point, then it means to get the maximum moment at this point, it will be this earth's pressure times the perpendicular distance. But since it is a UDL, you have to change first into a point load. So you will multiply. So it will be W times L. By doing so, you have changed it into a point load. Then the moment will be this times length, L again, and then the moment for a UDL, it acts at the center of that length. So WL times L over 2, you'll get WL square over 2. So let's punch our calculator. So this one is equal to 183 kilonewton meter. And remember, this one is acting, we are considering a 1 meter width of the slab. So 183 kilonewton meter per meter width, of the slab. This is the slab of the base, because this is a base, and we are designing it as a slab. So 183 kilonewton meter per meter width of the slab of the base. We now proceed to the ultimate moment. So the ultimate moment, or moment of resistance, is given by 0.156 FCU PD square. So we have FCU, we have B. What we don't have is D. So to get D, we will assume a 20 millimeter diameter bar. So assume millimeter diameter bar, and also assume a cover, of 50 or 50 millimeter, or you can obtain it in table 3.8 of BS8110. So assume 20 millimeter bar, 20 millimeter diameter bar, and also a cover of 50 millimeter. So we can obtain the D if we have the elevation. We can easily obtain our D. So this one is the overall H, which is equal to 600 millimeter. And this one is the cover, which is 50 millimeter. So our D is this distance. This is our D. And remember, this is our diameter. This is our diameter. So D is all the way from the top of the compression side to the center of these two bars. As you can see, this is the main bar. In fact, all of them will be of the same diameter because it is a square. So D, therefore D is equal to H, this H minus C minus diameter from here to here. So D is equal to 600 minus cover, which is 50, minus diameter is 20. So this one is equal to 530 millimeter. 530 millimeter. So that is our D. So you can easily now obtain our MU. So you can write here M is equal to 183 kilonewton meter. So MU is equal to 0.156. FCU is here, that 5. B is 1,000. B is 1 meter width of the slab. 1 meter width of the slab. So you convert it to millimeter. So you will get 1,000. Now times D. Our D is now 530 square. Then times 10 raised to power negative 6. Why am I multiplying by 10 raised to power negative 6? is because if I don't multiply by 10 raised power 6, I will get my answer in Newton millimeter, but I want my answer in kilonewton meter. So you multiply by 10 raised power negative 6. So the answer is equal to 1534 kilonewton meter. So since M is less than mu, then non-compression reinforcement is needed. So we will only design for tension alone and not compression. So main steel area of steel is equal to M 0.87 FYZ, and Z is given by this formula. Whereby K is equal to M FCU BD square. So this one is equal to M 183 times 10 raised power 6, change from kilonewton meter to Newton millimeter. FCU is 35 times B is 1000 times D 530 square, which imply K is equal to 0.0186. So this is our K. So Z is equal to D, which is 530, so Z, which implies Z is equal to 519 millimeter. 519 millimeter. And remember, Z must be less or equal to 0.95 D. So 0.95 times 530 is equal to 0.95 times 530, 504. Therefore, Z is equal to 504 millimeter. So you will use this Z, or we will use this Z as 504 millimeter. We now calculate the area of steel. So area of steel, use this formula. M is 183 times 10 to the power 6 all over 0.87 times 460 times Z 504. So this one is equal to 907 millimeter square per meter width of the slab. So that is our area. Now from table 3.22, now before you go to table 3.22, let's calculate our area of steel minimum. So A minimum is equal to 0.13% of BH. So this one is 0.13 over 100 times B is 1000 times H is 600. So this one is equal to 780 millimeter square. So area of steel is greater than A steel minimum. Therefore, okay. We now proceed to table 3.22 of BS8110. So in this table, you now convert this area into a bar size and a spacing of the bar. So provide Y20 at 300 millimeter center to center. Area of steel is equal to 1050 millimeter square, distributed uniformly across the full width of the footing, parallel to the XX axis and YY axis. This is clause 3.11.3.2 of BS8110. So you will see this in my sketch or in my reinforcement detail, that is for plan and section. We now proceed to critical shear stresses. Critical shear stresses. Allow me to rub here. I hope you know how to read the table. If you don't know how to read the table, come to the comment section. Just put their comment, write their comment, requesting me to help you on how to read the table 3.22, and I will help you how to read the table. But for those who have been following me, I know you know how to read it, so no need of wasting time repeating what you already know. So critical shear stresses. Critical shear stresses. So you have three critical shear stresses. You have the plunging shear, the transverse shear, and the face shear. So we'll begin by the punching shear. Punching shear. So if this is our column, if this is our column and this is our base, then the plunging shear will occur at that point. So this is the critical perimeter. So this is the critical perimeter. Critical perimeter for punching shear. And remember, this distance is 1.5 D. 1.5 D. Also here, 1.5 D. So now we are now supposed to calculate the critical perimeter for this column. So perimeter critical is equal to the perimeter of the column, plus 8 times 1.5 D. Why 8 times 1.5 D? Because this distance is the same all around this column. So it is the same here, it is the same here. So 1, 2, 3, 4 times the other side, that is 8. So perimeter of the column, remember our dimension of the column, it was 400 by 400 square. So perimeter of the column is 400 times 4 plus 8 times 1.5 times 530. So our D is 530. So the perimeter critical is equal to 7960 millimeter. 7960 millimeter. So this is our perimeter, our critical perimeter. So we now calculate the area within perimeter. So area within the perimeter, So this area is within the perimeter. So if this is our column, which has 400 millimeter dimension, so column is 400 millimeter dimension, and we need the whole of this distance from here all the way to here. So this is the distance we want, and also this one. So we will take 400 plus 1.5d times 2. So this one will be 400 plus 3.0d. So this is the distance from here to here. So the area is this. Area is length times width. So for this, it will be the square of this. So this one is equal to. So the area is equal to 400 plus 3 times d is 530, then square. So answer is equal to, this is 530. So answer is equal to, so this is 3.96 times 10 raised power 3.96 times 10 raised power 6 millimeter square. So that is the area within the perimeter. Now let's get the shaded area. This is the shaded area where the punching shear is critical. So the shaded area will be the area of this footing, of which it was 9 meter square minus 3.96. So the area of shaded part is equal to 9 meter square minus 3.96 meter square. So I have converted this into meter square. So you just divide by 10 raised power 6 and it will cancel. So this one is equal to 9 minus 3.96. 9 minus 3.96. This one is equal to 5.04. 5.04 meter square. So this is the area of the shaded part. The area of the shaded part. We now proceed to the ultimate punching force. The ultimate punching force. So the ultimate punching force will be ultimate punching force This one is equal to 217, which is our PS. That is the earth's pressure. 217 times 5. Remember, this is in kilonewton per meter square, times 5.04 meter square. So this will cancel with this. So this one is equal to 1094 kilonewton. So this is the ultimate punching force. The earth's pressure times the area of the shaded part, which is 5.04, and then you get 1094 kilonewton. We now proceed to design punching shear stress. Design punching shear stress. So this is V. Design punching shear stress, which is small v. So this one is given by V over perimeter, critical perimeter, times D. So our V, our small v is equal to, V is 10, 94 times 10 s power 3. You change from kilonewton to Newton over our critical perimeter. Our critical perimeter is 7960. 79. We have already calculated this, and our D is 530. So this one is equal to 0.26 Newton per millimeter square. 0.26 Newton per millimeter square. So this is our design punching shear stress. And then shear stress in concrete. So to get shear stress in concrete, we'll consider this formula: 100 AS over BD. So 100 times the area provided is 1050. 1050 over B is 1000 times D is 530. 530. So 1000 is 1 meter width of the slab. So this one is equal to 0.198. 0.198. And then from here, you will proceed with this value into a table of VC to obtain a VC for class 25 concrete, and then from there you can calculate for class 35 and compare with this, so that you can be able to tell if it is okay in shear or not. So let me show you the table. So this is the table. As you can see, values of design concrete shear stress, which is VC for FCU 25 Newton per millimeter square concrete. It is table 3.8 of BS8110. So we have column which has a value of 100 AS over BD and effective depth. So our value here, our value is 0.198. 0.198. So we'll come here and see and go for a value which correspond to 0.198, of which is not there. So we'll use the one which is slightly lower than that and slightly higher than that. So the lower is 0.15, and then we proceed to effective depth above 400. So this is 0.34, and then you come to 0.25, that is 0.40. So we will use these two values to interpolate and get our VC for 0.198. So this is from the table, as you have seen. So we have 0.15. So the value that is corresponding to 0.15 is 0.34, and then we come to value 0.198. So here is x. And then we have 0.25. We have 0.40. Then we'll get the difference between this and that. And then also this and that. So 0.25 minus 0.15 is 0.1. And then 0.198 minus 0.15 is 0.05. And then also get the difference between these two, and the answer is 0.06. Now you can do the comparison and get the value of x. So 0.1 you compare with 0.06 is equal to 0.05 over x, which imply x is equal to, we'll cross multiply and find the value of x. So which imply x is equal to 0.03. So to get the value, the value for VC in table 25, it will be 0.34 plus 0.03. So this one is equal to 0.37 Newton per millimeter square. But we want our VC for class 25 concrete. So this one is equal to 35 over 25 raised power a third times 0.37. So this one is equal to 0.41 Newton per millimeter square. So VC, our VC is greater than V. So V is 0.26 Newton per millimeter square. Therefore, punching failure is unlikely. So therefore, punching shear is unlikely. And a 600 millimeter depth of the slab is acceptable. What about if the VC was less than V? It means if our VC it was less than V, then the punching would have occurred. And what if the punching occurs? So these are the remedies, or these are the precautions you can use if the punching shear can occur when designing for basing for a footing of a column. So punching failure occurs when the concentrated load from a column causes the concrete slab or a footing to punch through, failing in a cone shaped around the slab. So what to do if it occurs? Increase the depth of the pad base. So if this depth was not enough, now you will have redesigned using another depth. Maybe you increase to 700, 800, etc. Remedy number 2, increase the plan area of the footing. So our plan area is 3 by 3 meters. Is 3 by 3 meters. So you can increase this plan. You can increase the plan maybe to 6 by 6 and so on. Remedy number 3, add shear reinforcement. You can also add shear reinforcement. Number 4, use a drop panel. Use a drop panel. And then the last one, improve concrete strength. So our concrete is class 35. You can improve even up to 40 and so on. So those are the remedies you can do if or you can apply if the punching shear occur while designing the base of a column. We now proceed to what we call a face shear. I told you we have 3 shear, that is the punching shear, the face shear, and the transverse shear. Let's now proceed to face shear. We now proceed to face shear. Face shear. So face shear, the maximum shear stress, maximum shear stress V max, in bracket V max, occurs at the face of the column. Occurs at the face of the column. So this, it implies V max is equal to W, which is the ultimate design load, over column perimeter times D. So our W, which was our ultimate design load, is 1950 times 10 to the power 3. Convert it from kilonewton to newton over the column perimeter. The size of the column is 400 times 4. Then times 530. So this one is equal to 2.3 Newton per millimeter square. And remember the permissible stress, the permissible is equal to 0.8 square root of FCU. So this is 0.8 times square root of 35. So this one is equal to 4.73 Newton per millimeter square. So therefore 2.3 Newton per millimeter square is less 4.73 Newton per millimeter square. So no reinforcement needed. We proceed to transverse shear, which is the last one. Transverse shear. Transverse shear. Transverse shear. So if this is the base of a column, or let's start with the column. This is a column, and this is the base. So our base is 9 meters square, which is 3 by 3 meters. So this is 3, and also here is 3. like that. And this is our column, which is 400 by 400 millimeters. So this is the transverse shear. Transverse shear will be along this edge, like that, such that this distance from here to here is D. So which imply if this distance is D, which is 530, then you can easily obtain the remaining distance. You can easily obtain this distance. So you remember, this was our plan, and if you have a section like this, so this is 3,000, and this one was 1,300. Also, this one 1,300, and the column is 400. So this distance, as you can see, from here to here is from here to here. So to get this distance, you'll take 1,300 minus 530, so is equal to 770 millimeters. So here is 770, like that. So let's proceed. So the ultimate shear force V, the ultimate shear force, which is capital V, is equal to load on the shaded area is equal to the load on the shaded area is equal to the load on the shaded area, and the load on the shaded area is equal to, and the load on the shaded area is equal to, remember our earth pressure, which was 217, times the area of the shaded region. So the area of the shaded region will be 0.77 times 3 meters. So this is the area of shaded region. This area from here to here is 3, then from here to here is 770. So 770 millimeter, you convert it to meters, you'll get 0.77. So this one is equal to 501 kilonewton. 501 kilonewton. So the shear stress V is equal to V over BD. So this one is equal to 501 times 10 raised to the power 3. Change it from kilonewton to newton. Our B is 1,000 times D is 530. So this one is equal to 0.32 Newton per millimeter square. So this 0.32 is less than VC. is less than VC. Remember our VC, it was or is 0.41 Newton per millimeter square. So therefore, hence no shear reinforcement is required. Hence, no shear reinforcement is required. So what is remaining on this question is the reinforcement detail for plan and section, and we will have done with this question. So I want to proceed to reinforcement detail for plan and section. And this is the last part of that question. So this is the reinforcement detail, this is the plan, and this is the section. So if you cut across this plan as indicated AA, so this is what you will see. So that marks the end of this question. So if you have any question, you can ask me through the comment section and I will be able to answer your question. So if you have not subscribed to this channel, please subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. So thank you for your time, and we meet again in my next session.